Chapter 8 is all about chain rule. Chain rule is the last of differentiation rules and will complete our collection that so far consists of sum rule, difference rule, product rule, and quotient rule. Let's think about functions in general first. So if I were to take derivatives of any one of these, I have to think of the algebraic structure of the function, so I'm able to decide what differentiation rule to apply to the scenario. So for example, this first function is a sum of two functions, so I will be applying the sum differentiation rule, which essentially says that I can take derivatives of the functions that compose the sum separately. The second function here is, of course, a product, and therefore, if I were to take a derivative of it, I would have to apply the product rule. This next one is a quotient, which will then call for quotient rule. And what about this last one? So inside of the seventh power, it's a sum, but outside here, it's the power. So how can I classify this function? Is it a power function? Is it a sum and then a power? Well, this is essentially exactly the problem, is that this function is a composition of more functions than just one. And we need to be able to break it back down in order to figure out what its actual structure is. So this is going to be an incredibly fast review of function composition. If you need more of a refresher, please go take a look at the pre-calculus review package. There's a section on function compositions. Generally, function composition, we think about it as a one step at a time process. So let's take a look at this function, x plus 3 all squared. If I were to give you a particular value of x, what would be the first operation that would be applied in calculating x plus 3 squared? Well, first of all, you will be adding a 3. So the first function that gets applied is an add 3 function. And the output here will then be x plus 3. And then once we have that computed, we will raise the whole thing to power 2. So the next function that gets applied will be to square it function. And result here will be x plus 3 squared. Now, as opposed to giving them verbal names like add 3 and square, I can also give them much shorter names so that I can use the function notation. So let's say the add 3 function will be called f, and the square function will be called g. Then we notice that if I were to rewrite x plus 3 squared, what happened to x first, so let me write on this right-hand side here, is I took my x, and the first function I applied to it was the function f. So the first thing to act on x was f, and then once I had the output for that, I applied the function g to it. So afterwards, we applied g. So notice that the functions here get applied from inside out. I start with x, and then I build up layers of functions on top of it. The order here matters a great deal because g of f of x is not going to be the same as f of g of x. So in this case, for example, f of g of x means that I first took x and applied the g function, which was to square it. So first I had x squared, and then I had to apply f to it. So my outcome here will be x squared plus 3. Now, of course, x squared plus 3 is not the same as x plus 3 squared. So the order in composition really matters. The other thing that I should mention here is the notation that we use for function composition. So writing this out is a full way to write this out in function notation. The other way to write this out, so for example, if I have f of g of x, is to use this little circle in the middle. So this is what we would read as f composed with g of x, or f of g of x. Okay, so with this in mind, the chain rule states that if I were to take a derivative of a composed function f of g, I have to take a derivative of the outside first, followed by the derivative of the inside. So I tend to think about that as an onion. If you're peeling an onion, you're going to have to take an outside layer first, but the inside stays put. So it's the same thing here. I take a derivative of the outside function, but the inside function stays the same. when you're taking the top layer of your onion off, you cannot affect the middle of the onion. The middle stays the same. But once the top layer is off, you have access to the middle, so you proceed to then take a derivative of the middle. So this is generally going to be how chain rule works too. We're first going to take the derivative of the outside function, keeping in mind that the inside stays the same, and then follow by taking the derivative of the inside function. So in all of the chain rule problems, the first and the key step would actually be to determine what is the outside function and what is the inside function. So far, we have only worked with polynomials, and with polynomials, it's actually going to be fairly easily to figure out what's inside and what's outside. So here, if you have to think of how does the composition occur, so if I did pick a particular value for x, and I went through to actually calculate this expression, then the first thing that is going to happen to x is I'm going to compute the value for x squared plus 5x. So this is my inside function. And once we've computed that, we're going to raise everything to power 7. So that will be our outside function. It is helpful here too that the inside is physically on the inside of the power. So in this case, it is quite visible. We will see some slightly more obscure examples very shortly. Okay, so according to the chain rule, I have to first take the derivative of the outside function while keeping the inside intact, and then take a derivative of the outside function. So let's do this carefully. So my derivative is, first I take derivative of the outside function. Outside function is the power 7. What is the derivative of something to power 7? So in particular, what is the derivative of x to power 7? Well, this is just power rule, so this is 7x to power 6. So it's going to be the same thing here. The power rule tells me that I need to take the power, bring it down to the front, and reduce the power by 1. But keep in mind that the inside of that function has to stay what it was. So I'm going to bring the 7 down and reduce the power by 1, but the inside has to stay put. And the inside was x squared plus 5x. Okay, so this is the derivative of my outside function. And then I haven't dealt with the inside yet, and now is the time to do so. Once you've taken that outside layer off, we have access to the inside, so I now have to follow by the derivative of the inside function, right? So now is where I look inside. The inside is x squared plus 5x, and so I take a derivative of that, which is 2x plus 5. So this is the derivative then of the inside function. So let's take a look at a couple of other problems, some of them which will involve other differentiation rules that we've already covered up until now. So the first function here is the same as on the previous slide, but then we have functions that somehow build up on it. So 4 times the same function, and then 4x times the same function. So what are we going to do now? How are we going to take a derivative of this now? It is no longer just one inside and one outside. There's also this factor of 4 present up in the front. So it's useful to remember here the constant multiple rule. If I have a constant times a function, then I can leave the constant alone and take a derivative of the function. So this 4 can stay there, and then I just need to take a derivative of whatever remains. Now in this case, that's lucky because this is the exact same function, so as above, so my derivative can be taken from there. So if I were to write this out fully, this would be 4 times 7x squared plus 5x to the 6 times 2x plus 5. There we go, squeezed it in. Okay, the next case is 4x times this function. So in itself, this big function is actually a product of 2 things. So this is one key thing to notice right away, is that if it's a product before it's a chain rule, then I have to apply the product rule first. So here I have a product of 2 functions. So the first rule I have to apply is the product rule. So the derivative of c here would be, recall the product rule is, it's the derivative of the first function times the second function plus the first function times the derivative of the second. Okay, and once you have that, the derivative of 4x is just 4. This stays the same. Then we have 4x, and then we have a derivative of this function that will require us using the chain rule, but it's the same function as above. So we already know how to do that. Okay, so I'll leave it up to you to fill in the next line. Same idea for the next question here is that, first of all, it's a product of two functions. So the first thing I'm going to do is apply the product rule on the two separate pieces. But then my two separate pieces, the first one is just x squared, so that's fine. I can take a derivative of it when I have to. But the second one is 1 minus x all cubed. So the second piece in itself has an inside and an outside, right? So this is then the outside function on that portion, and this one is the inside function of that. Okay, so going through with this, I'm going to write out answers in a second, but please pause here and actually think about what you would get as the answer. Okay, so this is actually the outcome. This is the derivative of x squared followed by the function as per product rule, plus x squared left alone followed by the derivative of 1 minus x all cubed, which is a chain rule. So the power came down, got reduced by 1, while keeping the inside intact, and then I have to follow by the derivative of the inside. The derivative of 1 is 0, the derivative of minus x is minus 1. So this is where this factor of minus 1 comes in. Okay, and for the last question here, again, first take a look at it and figure out what kind of function is this. In this case, it looks like a quotient, so you can apply the quotient rule. That's one way to go. The other thing to maybe notice is that while it's a quotient, the top is just a constant. So I can actually rewrite this whole thing as a power. So it's the power of a cube root on the bottom. The cube root itself is a power of 1/3. It being in the bottom means it's negative. So this whole thing is actually equal to x squared plus 6 to power minus 1/3. And then I can, depending on which route you chose, you can either proceed with the quotient rule or you can proceed with a power rule on this function. Now, of course, the power rule in this case will also involve this as the outside function and this as the inside function. This is a really great example to practice on, so please continue the work here to actually get the final answer. Now, these are just mathematical functions, but chain rule is extremely useful in applications and actually arises quite naturally. So let's take a look at the first one. The population of wolves depends on the population of elk. The elk population, in turn, depends on the abundance of vegetation, which in its own turn depends on the amount of rain of any given year. So you see how this chain of events or chain of dependency is built through the natural cycle of life. We would like to quantify the rate of change of carnivore population with respect to rainfall. So keywords being here, rate of change, which means that we're talking about a derivative. But before we have something to take a derivative of, we need to actually find what that function is. So let's work through this chain. So I have that the wolves depend on elk, which depend on vegetation, which depend on rain. So wolves population is actually a function of elk population. The more, let's say, elk, the more wolf there are. Elk depend on vegetation and so on. So in function notation, I can write this as W of E of V of R. And now I just have to make sure I have enough brackets closing. I think that's about right. Okay, so this is the full chain of dependencies in this situation. The chain rule is called that because you take derivatives in this specific chain, right? So if I were to take a derivative of this function now, so let's say I am taking this function in this function notation, and I would like to take a derivative of it. The chain rule says that you first take a derivative of the outside most function while keeping the inside, and then proceed to work your way in. So the outsidemost function is w. So I will first take a derivative of w and keep whatever inside it has. I'm going to leave it blank for now so I don't have too many letters. So first I take a derivative of w, then I have to take a derivative of e while keeping whatever inside it has. And then next I have to take a derivative of v while keeping whatever inside it has. And now I'm out of variables, r, right? That's kind of like my x in the previous example. I can follow up with r prime here, but that's just going to be 1. Okay, and now that I can clearly see the structure, I can fill in the blanks with the insides of the corresponding functions, just to make sure that I didn't lose anything in the process, right? So the inside here will be e of v of r, which is the inside of the original w function. The inside of e prime will be the inside of the original e function. So this will be of v of r, and the inside of v prime is just r, okay? So this is the entire derivative and how you would take it. Now, the problem is this notation is not only now looking pretty bulky, but it's also making one fact really not clearly articulated, and that is the fact that when I take a derivative of w here, what am I taking it with respect to? Now, the thing in our chain of command here says that w, the wolves, depend on e, the elk. So as far as w is concerned, its independent variable is e. So when I take a derivative of w here, I am doing so with respect to the elk population e, okay? But because all of these variables are present on the inside of the w, it might be difficult to track that. So this is also where the other notation for derivatives might come in much handier, as it would in actually many word problems. So instead of stating the derivative the way that we did, I am going to use the notation that we've discussed earlier, which is df by dx notation. So in this case, I would like to quantify the rate of change of carnivore population, which are wolves, with respect to rainfall, which is r. So this notation makes it immediately clear what is it that I'm taking a derivative of, and what is it that I'm taking a derivative with respect to. And now the chain rule tells me that I have to go through all the layers of my chain to get from w all the way down to r, okay? So the first step here is I'm going to take a derivative of w with respect to e, its independent variable. So the first derivative is w with respect to elk population. And then the chain rule is a chain of multiplications. So followed by times, and then I follow through with the chain. So now I'm at e, I have to take a derivative of e, and its variable is v. So I have to take a derivative of e with respect to v. And now I'm at the v step, so I'm right here. I have to take a derivative of v with respect to r. And this brings me to the end of my chain, so I know I'm done, okay? So this is what the derivative would look like in this notation. The other thing that's actually really easy to check here, I mean, there's lots of really good reasons to actually use this notation as opposed to this one. For word problems, this notation will much easier let you know what the units are, because you have naturally the numerator and denominator, so you will be able to read off the units for the numerator variable and the denominator variable, but also, particularly in the chain rule, it will really let you know if you've done it right. Because in the end, look, if you treat it for a second like quotients, that they are in the limit, then you can notice that, for example, this DE and this DE cancel. They don't quite cancel. You can't actually cancel them out because each one of those things is a derivative and not a real quotient. But at least in terms of units, you can follow this logic. So the two DEs cancel out, the two DVs cancel out, and all you have left is dW by dr, which is exactly the thing that was required on the left. So you can make this sort of common sense check to make sure that you've actually covered all the steps of the chain correctly, which is something that you cannot easily trace through the prime notation here.
So at this point, we have seen the analytical and the verbal description of the chain rule. Let's move on to take a look at the graphical and then the numerical applications of the exact same rule. So here we have two functions, f of x and h of x, given by the graphs. So this is the graph of the function f of x. This is the graph of the function h of x. We are not given formulas, although you can derive them at this particular point. But the idea here is if you are given a graph, then you will proceed through the solution of the question by using graphical information only and by interpreting the derivatives or finding out how to apply various differentiation rules by analyzing the graph. So first of all, we're asked for f prime at 3. So the derivative of the function f, given by this first graph, at the point 3. Remember that the derivative of a function is the slope of tangent line at the point of interest. So in this case, f prime of 3 is the slope of tangent line to the function f of x at the point x equals 3. So now let's take a look at our graph. This is x equals 3. So this is the point of interest. What is the slope of the tangent line at this point? Well, this is the corner point. And if we try to construct a tangent line, we won't be able to do so because it's not going to exist at this point. Is the tangent line going to go this way? Is it going to go this way? How can we attach the tangent line to the graph? Remembering that the tangent line is the secant lines getting closer and closer together. This is impossible to do at a corner or a cusp. That is exactly where the function is not differentiable. So in this case, the slope of the tangent line is impossible to calculate, and therefore the derivative at 3 does not exist. Next up, we are defining a new function, g of x, that is f of h of x. So f of h of x, using the function composition here, and we're asked to find the derivative of this composition function at 2. So first of all, let's ignore the fact that we're interested in a particular point and find the derivative of this thing algebraically for any x. So this is combining, first of all, the algebraic interpretation of the chain rule, and then using the particular point and the graphs to compute the derivative at the specific value. So by the chain rule, if we have a composition of function, the chain rule says that in order to compute the derivative of this, we're first going to compute the derivative of the outside, leaving the inside intact. So we're not changing the inside first. And then follow it up in a chain of multiplications by the derivative of the inside function. So here, the outside function is f. So first I take a derivative of f, leaving the inside as it was, peeling the layers of the onion one at a time. So I've dealt with the outside layer, and then I followed up with the derivative of the inside, which is something that I have not up until that point yet considered. Now we're interested at g prime at 2. So all I have to do for now is rewrite this entire expression and replace x with 2, because that's the value at which I am going to consider my derivative. Okay, now I need to actually figure out what these numbers are. So let's take a look at what we're after here. So first of all, this guy, f prime of h of 2. So the very first thing to do is take a look at the inside here. H of 2 is something I can read directly off of the graph of h. H of 2 is going to be the y-coordinate of this point, which is equal to 4. So h of 2 is 4, which means that this entire expression now turns into f prime at 4. Okay, so let's rewrite that first. F prime at 4 times, I haven't changed this second factor, so I'm going to just rewrite it. H prime at 2. Okay, now I have to figure out what these two separate values are. So let's take a look at this first one here, f prime of 4. Using the same logic as we did in part 1 of this question, we're going to recall that the derivative of the function is the slope of the tangent line at the point of interest. So this is going to be the slope of tangent line at 4, and h prime of 2 is going to be the slope of tangent to the function h at 2. So notice that we do have to keep it straight which function is which, right? This one is going to be the slope of the tangent line to the function f at point 4. So I'll be looking at this graph. And the second one is going to be the slope of the tangent line to the function h at 2. So I'll be looking at the second graph. So let's see. For the first function, the derivative at 4 is the slope of a tangent line at 4, which is this point here. And this is where our function is linear, so it's going to be just the slope of this line, which I can calculate by taking the rise over run between any 2 points here. And if you plug it in, you should see that that particular slope is equal to -2. I'm going to keep this color-coded as I did in the description. And h prime of 2 is the slope of the tangent line to h at point 2. And at this point, the tangent line is also the function itself because the function itself is a line. If you calculate the slope here, you will see that it's equal to -0.5. Multiplying the two numbers together will give me 1 as the final answer. So let's review this procedure just for a little bit to notice all the important steps here. First of all, I was given a composition of functions using the analytic or formulaic notation, which meant that my first step, I applied the chain rule onto the actual formula by taking the derivative of the outside, keeping the inside intact, and then taking the derivative of the inside function. Once I've done that, I've plugged in my point of interest and then used the graphical interpretation of the derivative to actually compute the corresponding values for the numbers. Okay, multiple steps to this problem, but nothing too dramatically different from the things that we have done before. Okay, let's take a look now at what happens with the chain rule applications if we are given our function numerically or using the table of values of some sort. So here I have the two functions f and h, and they're given to me by the table where I have both the function and the derivative values at different points of x. So the way that we would read this table is if x is -1, then these in the first row are the values that correspond to f of -1, f prime of -1, g of -1, and g prime of -1. Okay, and the same for 2. So both of these are actually function compositions. So we will use a similar approach as we did on the previous slide in part 2. I'm going to write this out first using the chain rule in the formulaic notation, and then I'm going to use the table to actually try to evaluate my numbers. Pause the video here and try to proceed by yourself. There's nothing on the slide that we haven't already seen. Okay, so for the first one, if I take a derivative in general, I need to take a derivative of the outside function first, leaving the inside as it was, so just g of x, and then follow by the derivative of that. Once I have this, I can actually just take this expression and copy it over and replace my x with the number at which I'm interested in computing the derivative at. So I'm going to replace all of my x's with the number 2. And now I'm going to use the table to look up the values that I need to actually plug in. So first of all, working inside out on this function, g of 2 is equal to what? Well, this is the column for g. This is the row for 2. So g of 2 is equal to -1. So overall, so far, I have f prime of -1 times g prime of 2. And now I just have to look up these two values in my table as well. So f prime of -1, f prime and -1, it will be a -5. And g prime of 2 will correspond to g prime of 2 will correspond to this value in the table. So g prime of 2 is going to be 2. So overall I get minus 5 times 2, which of course is easy enough arithmetic. I can do in my head, is minus 10. Fantastic. Next question is very similar, except my two functions are the same. So we got to keep it really straight with the chain rule here. So k prime of x, what are we going to have? Applying the chain rule in the exact same way before, I'm going to take the derivative of the outside first and then keep the inside intact, following by the derivative of the inside. Okay, the fact that it's the same function does not affect the application of the chain rule. It's applied in the exact same way as if the functions were different. And then, as before, I'm going to take the same expression and I need to calculate this at -1. So I'm going to replace my x with -1 throughout. Okay, -1, -1. Perfect. So, working my way from inside out again, f of -1 is going to be equal to 2. So what I'm going to have is f prime of 2 times f prime of -1. And computing these two values from the table, I will notice that I get 4 times -5. Make sure that these numbers are correct, and you can in fact find them within the table. And so, of course, multiplying the two together, I'm going to get a -20. Fantastic. These were the graphical and the numerical or tabular representations of the function and the application of the chain rule to them. Now let's see how chain rule can work in applications. So a little bit more of the verbal and the interpretive applications here. So let's see what we have for the first example. Carbon monoxide pollution in the air is changing at the rate of 0.02 parts per million for each person in a town whose population is also growing at the rate of 1,000 people per year. So each person contributes 0.02 parts per million, and the number of people itself continues to increase at the rate of 1,000 a year. We're asked to find the rate at which the level of pollution is increasing with time. So let's take a look at what are our moving parts here. First of all, we're asked for the rate of increase of pollution. So let's start to figure out what is the actual process by which that happens. We notice that the pollution is changing at 0.02 parts per million for each person. So per person, right? It's important what the units are here. And then this is followed up by the fact that the population, so the number of persons, is also growing at the rate of 1,000 people per year. So the pollution per person is then multiplied by the number of people contributing to that pollution, right? This happens per person. And how many people are there? Well, there are however many people there are, and they're increasing at the rate of 1,000 people per year. Or let's call them persons, just to keep English the same. Persons per year. So what do we have here in terms of units? Let's see if the units check out. Well, there's persons on the bottom and persons on the top, so these two numbers will cancel out. And in terms of units, we will end up with parts per million per year, which of course does make sense in terms of the rate of increase of pollution. So our physical number here is going to be 0.02 times 1,000, so 20. And in terms of units, we're going to get parts per million per year. So the units make sense, and therefore this seems like the right approach to take. Let's try to generalize this idea and introduce the function notation to it. So let's say that my pollution level, which is something that I'm interested in terms of how fast it's increasing, the pollution level is going to be labeled as L. And what I noticed that is that the pollution level is a function, of course, of the population size, which is also a function of time because it is increasing with time. So let's follow through this sort of chain of command here. Pollution level is a function of population size, So maybe let's give population size a variable as well. Let's call it P. And the population size itself is a function of time because it is changing with time. And time ordinarily gets called T, L. So overall, we have that my pollution level L is a function of population size, which is a function of time. And this is my composite function here. So if I'm interested in the rate of increase of pollution, that of course means that I'm interested in the derivative of the pollution. So I am interested in the derivative of this function that I have just built up. So taking this all together and using the prime notation, what are we going to do in terms of the chain rule? Well, the chain rule says take the derivative of the outside function, keep the inside intact, follow by taking the derivative of the inside function itself. And this is where we see the exact same two components we've had before. The increase in the pollution when we're keeping the population sort of fixed is 0.02 parts per million per person. The change in the population is 1,000 persons per year. So these are our two factors. The other way we can rewrite the exact same thing is using the Leibniz notation, the dl by dt. Again, this would be much more useful in terms of units, and we're going to have to go through the levels of the function. So if I want to take the derivative of L with respect to the innermost t, I have to work my way there by going through p. So first, I can take a derivative of L with respect to p, which corresponds to this factor. So dl with respect to p, and then follow it up by taking the derivative of p with respect to t. So dp by dt. Okay, and all of these things actually stand for the exact same value. The increase of the population of the pollution with respect to population. Okay, with respect to population, with respect to population. So once again, I know that generally everybody prefers the prime notation, but the Leibniz notation is much more connected to the units. And this is particularly useful if we're talking about word problems. You notice that parts per million, which is the measure of the pollution, per person, which is the measure of population size, followed up by the rate of change of the population, which again, in all of these notations corresponds to the same value. And again, the Leibniz notation tells us it's the population counted in persons per time unit counted in years. Leibniz notation is also useful, once again, if you think about this as quotient of various values, you can notice that the p's will quote-unquote cancel out. Not actually, but in terms of units they would. And what we're going to get is dl by dt, which is corresponding to what we actually have on the left-hand side as well. Okay, so this is what we have in these types of applications. Let's take a look at one more example here in terms of applications. So we've seen this function before. The predation rate of wolves on moose in North America can be modeled by this function f, which is measured in moose killed per wolf per 100 days. And x itself is measured in the density of moose per square kilometer, so number of moose per square kilometer. Here's the information that we're given. If the current moose density is 0.5, so there is half a moose per square kilometer, not physically, but on average. And we know that this number isn't static. It's in fact increasing at the rate of 0.1 per year, whereas to determine the rate at which the predation is increasing. So we notice again a chain of various dependencies here. The population of wolves, the predation rate of wolves depends on how many moose there are per square kilometer, and the number of moose per square kilometer is changing with time. So Pause the video here and try to write down in which way which functions depend on each other. So overall, that means that if I build my function f, I have it depending on x, as in fact was already given, but my x also depends on time t. So I have myself a nested function once again. We are asked to compute the rate at which the predation is increasing. Predation is f, so we are asked to compute the derivative of that. F of x of t all primed. Okay? And once again, we can apply the chain rule. I'm going to actually write all of this out in terms of the Leibniz notation, so we're able to keep track of the parts that are going into that as well. So once again, I'm asked for the derivative of f with respect to the innermost t, which means I'm going to have to make my way there through this middle variable x. So first, I'm going to take a derivative of f with respect to x. So df by dx, and then I can take a derivative of x with respect to t. So dx by dt. Let's pause here and do a little check. If I cancel out these x's, I'm going to get df by dt, which is the left-hand side, so I'm in good shape here. Okay, so now let's take a look at these separate parts. What I have here is df by dx, the derivative of f with respect to x. And the function f here is given to me directly in terms of x. So all I have to do is actually take a derivative of that with respect to x. We can apply the quotient rule or whatnot. I'm going to just write down the actual answer. It's going to be 3.36 times 0.06 divided by the denominator squared. So this is coming directly from the quotient rule. This is df by dx or f prime of x. Just making sure that we're getting comfortable with all of the notations here. Okay, this is the first part of this multiplication. What about the second part? Dx by dt. Let me rewrite it first, and then let's think about what its value is going to be. So this is how fast the mousse density x is changing with respect to time. Okay, we are told that the rate of increase is 0.1 per year. So that means that this value is going to be 0.1 mousse per year. And the last piece of information we have not yet used is the fact that at this particular point of time, we're told that x is equal to 0.5. So this is the value that we're going to be able to plug in here. So plugging in x equals to 0.5, we're going to get at our final answer. So let me rewrite it using all of the algebra that I have here, just so we have on record where everything went. And then calculate this as the final answer, which is going to turn out to be approximately 0.167. Now, because it's a word problem, we would like to think about what are the units. Remember that F is the predation rate measured in moose killed per wolf per 100 days, and T is measured in years. So once again, Leibniz notation to the rescue. We're going to have on top moose killed per wolf per 100 days, and on the bottom, we're going to have per year. Yes, we're going to have a little bit of complication with the units of time, but that is what our function was given to us as, and so that is the actual units that we're keeping. Make sure that you understand how to construct the chain of the dependencies and how to then carry through the chain rule using either the prime or the Leibniz notation.